look at a star in the sky, it captures concepts of the particle and concepts of the wave.
Because it's an object and it's also emitting waves.
That's right. So we really have a world full of energy, fragments of energy, and we have the source of the energy captured historically through the particle, and we have the radiation historically captured through the electromagnetism in one concept, fragments of energy.
So we've talked about the crisis. Let's back up. Let's talk about particles.
Okay, so let me give you a little bit more complete description of what happened with the particles. So it really starts in 1687 with Newton's Principia. Okay, this is a book that he writes, okay, where you have Newton's first law, second law, and third law.
Yeah,
and
we all know those.
And his universal law of gravitation. So that is the book where he introduces all of that. And that is where you really get particles, and that's where you get today we call the field of mechanics. Okay? And what law 1 says is that if you have a body, okay, so this is kind of the rules of what a body is. The law 1 says if you have a body and there's nothing else affecting it, it's just going to go in a straight line at a constant speed, okay, in an inertial frame. And
what's that inertial frame?
Inertial frame means a frame that is kind of stationary, stationary, not moving,
okay,
or moving at a constant speed itself. Okay. And in fact, that in itself is clarified later on after Newton. Newton himself never really said what the inertial frame is. He just said it's got to be a frame that's actually just not moving. But in any event, in that frame, things just move in a straight line at a constant speed, and that's his first law.
And is that in a vacuum?
It's if it's not acted upon, it's a vacuum.
I guess.
So in other words, it
would have to be an active theoretical space.
Yes, because if it's not in a vacuum, those particles might be slowing it down or something like that. So it's kind of a theoretical idea.
While we're off the topic, is space a vacuum?
Space is a coordinate system.
Okay.
A frame of reference.
If you threw a rock in space, would it eventually stop?
If there's nothing acting on it, theoretically, it just keeps on going at a constant speed.
Okay.
It's a model. Remember? You're asking me, what is really happening?
I need to know, Larry.
Well, see, this is the model. This is the issue between a model and reality. Right?
Yeah.
So it's just a model.
There's no model that will ever truly model reality.
That will get it perfectly, you mean?
Yeah.
That's actually a whole big philosophical discussion by all these scientists who actually are really deep.
They want to figure it out.
And this is a whole question of fate.
Oh.
There's this whole question of fate, because if it's all can be predicted, there's no decision making. It's all going to happen.
It's just there.
It's predetermined.
Yeah.
So particles start with Sir Isaac Newton. He writes a book called Principia in 1687, Newton's first law, which says that in absence of any other external body acting on this one body, it'll just keep on moving. Keep on rolling at a constant speed and direction. His second law states that this other body is going to change the path of that first body through forces.
Okay.
And those forces are going to change the speed and direction of the body.
Okay.
A change over time of a speed and direction of a body is called acceleration.
Okay.
So what he's saying is that the force acting on that other body is going to give that other body its acceleration, is the cause of its acceleration or the change in its speed and its direction. And his third law gives rules about those interactions between the bodies. He says if one body A, acts on body B, okay, body B will have to act also on body A. They'll mutually act on each other.
There's an equal and opposite reaction.
Exactly. That's his law 3.
Yeah.
That's right. And not only will they act in the same magnitude but in opposite directions, but they'll act along the line between the two bodies. So if you have one body over here, another body over here, you drew a line between the two, that's going to be the line of action of those forces. If you're good in pool, you got to make sure you line things up.
There you go.
Exactly. And actually it's even in basketball, which I like.
Yeah,
also,
absolutely.
So that was Newton's third law. And then his universal law of gravitation, the fourth law, is where he says if you have the earth and the sun, for example, okay, there's going to be a force between them, and that force is going to be inversely proportional to the square of the distance between them. So if they're farther away, the force will be less, and it's proportional to the product of the masses of the two particles. Okay?
How do you measure that in 18 whatever?
Oh, you'd be surprised.
How do you come up with that?
Well, actually, it's a long answer, but we first had to know what the distance is between the Earth and the Moon, okay? In order to get, let's say we're talking about the Moon orbiting the Earth. then we would have to know the distance between them, and there's ways of calculating those distances. Then from our formulas for acceleration and how long it takes for the moon to orbit the Earth.
Probably took a while to figure that out, right?
Okay, we had all of these different people actually had figured all these things out. In fact, the answer to your question is what led Newton to his laws, because he took the calculations that different people did, and he realized that force equals mass times acceleration. If you start with that, you'll get all these other results that people had figured out already. Yeah.
Wow.
Yeah. So that was kind of part of it.
Because I think part of understanding science for the average person is always asking how'd they do that? How do they know that? And so hearing those things help.
Oh yeah, there's lots of little experiments that people do in order to arrive at that. But the most important thing about the particle, though, is that it really represents a body, and that the universe, and it creates this wonderful image of reality of these bodies, the universe being made up of these bodies, but in between there's nothing. And then there's these mysterious forces acting between them that make them, instead of moving in a straight line, that make them deviate from moving in a straight line. And that becomes this mechanical image of the universe.
Okay.
And that's basically particle mechanics.
Okay. So we're talking about these theories from a long time ago. Why are those important to our understanding of modern physics?
So the particle is one of the major pieces that's important to modern physics. That's that was the particle. And that was one conception, this mechanical universe made up of bodies, nothing in between them, all exerting forces on each other. But there are all sorts of paradoxes, like how does the force get from one body to another? It doesn't really make much sense. So this is that mechanical view that has things that are about it that we can't answer, that has these paradoxical things. So that's the first part of it. The second part of it comes 150 years later, where we start to develop a different type of science, which is electromagnetism.
So 150 years, that's a pretty long time to rest on the particle science, right? How revolutionary was that when Newton came up with those laws?
I think it was revolutionary in the sense that he was putting together what other people were doing and could explain it for the first time in a way that everybody could understand. So it was extremely revolutionary, and because he could explain it so well, it spread.
Okay.
The 150 years...
It made sense.
Because it made sense. The reason there's 150 years between Newton and Maxwell is the originator of electromagnetism, and he's the one who writes the book that makes sense too, 150 years later, involving electromagnetic waves. The reason there's 150 years between them is because the math had to catch up. We didn't have the proper mathematics to be able to mathematically describe electromagnetic waves. That was one of the big problems. The other problem was a discovery that Maxwell had made.
Which was what?
Well, he discovered that magnets, electricity, and optics all radiate waves that are traveling at the speed of light. And so it was this eureka moment where he realized that, wait a minute, there are these three branches of science called electricity, magnetism, and optics, but all of them involve these bodies that are giving off
energy,
either light.
Yeah.
They're giving, if it's a magnet, it's giving off some effect that will move something else. Okay, or if it's electricity in a wire, it's giving off these effects that make other bodies move. And all three of them were transmitting their information at the same speed, all at the speed of light. And
wow.
He thought, wow, they are all electricity, and optics and magnets are all electromagnetism. And so electromagnetism is born, recognizing that bodies all radiate at the speed of light.
So does electricity move at the speed of light?
Not necessarily, the sources don't,
okay,
but they radiate out.
Oh, okay.
What radiates out is moving at the speed of light. The information is going from one body to the other at the speed of light, if you time it.
Wow.
So he realized that all of these are very, very similar. And so he brought those three fields together, and that created this second field, electromagnetism. We already had this field of mechanics. It didn't bring together mechanics, but mechanics was out there. Now we had electromagnetism, and now we're seeing physical reality with these two ideas, which are very different.
What usually comes first, technology or science?
Technology. You tend to have the technologists who see an opportunity and want to turn it into an invention. And the biggest invention that makes a practical invention, and the first invention really is the telegraph. The telegraph is what makes electricity popular throughout the world. Okay, we can now communicate in minutes instead of in days and months.
Was that Bell?
No, there's a number of them that do this, But Bell comes a little bit later with a phonograph and other inventions, the light bulb and things like that. That's Edison.
Edison,
Yeah. So anyway, so electricity takes off. But while this is happening, you also have scientists who are not technologists, but they're asking why. What is this?
Why does it work?
So it really depends on the person. Some people want to turn it into practical things.
Let's make money.
Others are like, what's really going on here?
Right, because there's more. What else can we figure out?
Yeah, that's right.
What was the thing that bridged the particle science into now what is the wave science, the electromagnetism? What was there a piece of technology that was invented that started Maxwell's journey?
So the field of electromagnetism actually starts out with scientists thinking that it's actually part of particle mechanics, but then they realize it's not part of mechanics, that we actually have these waves. But it actually starts off trying to absorb it into mechanics, but they couldn't
figure it out.
They just couldn't figure it out. And so what ended up happening is it kind of just moved away from mechanics and became its own theory. And the folks who are looking at electricity are they're a different group of folks. So you actually have a whole set of scientists who are really just looking at electricity. And at that point, really, you have two different groups. You have folks who work on mechanics and folks who work on electromagnetism or optics and magnets and all of that.
Silos?
And they are really silos, yes. They're really different groups of people. And so what you really have is an evolution of two different types of scientists, and they really are different communities.
Okay, yeah, so we have two things kind of rising up separately. Both work, both have practical ramifications. But at that point, everyone's okay with the gap.
Well, I think even earlier on, there were people who recognized that there must be some connection between them, that there shouldn't be two different explanations for reality, but no one could figure it out.
Okay.
And so you really had kind of in order to figure it out, you really had to have the right math for it.
Right.
So
is that what makes science? Is that what gives it the green check? If you can do a formula that equals the right thing, then we know it works.
Yeah, the mathematics gives you kind of the validation that everything that you're thinking actually works out, because you're starting off with these assumptions that are very basic.
Yeah.
Then you're using the mathematics to test it out to see if it's all
predictable.
And the math is what makes it gives you the ability to extrapolate from the principles to be able to see if it works out in all sorts of situations. And if it does, you verified it. If you don't have the math, you can't really verify it. So when we went from mechanics to electromagnetism, there's over 100 years where the math has to develop, the calculus has to develop into fields, including acoustics and other fields. And then eventually we can actually describe distributions. Electromagnetism is a little bit more difficult mathematically to describe because you're talking about distributions, not just a body that's moving like a projectile. So it was more complicated.
It makes sense why it took so long.
Yeah. And then now you're trying to reconcile it. So now you get to another stage where you have to reconcile it, and you have to try to put these two ideas together. So this is what we're left with. That's the legacy, the history that we're left with in our schools. We have particle mechanics as classes, we have electromagnetism as classes, and they're separate classes, and as if they're separate realities.
Yeah.
And so this is kind of the legacy that we have right now. And now the modern physics.
Okay? Kind of?
Well, it's all progress.
Yeah, sure.
So it can be better. So modern physics can actually bring those together. And with modern physics and with new ideas, we don't necessarily have to have these two different separate ways of thinking about things. It's kind of analogous to, there's a little bit of an analogy here. So the ancient Greeks with their earth, water, air, fire, and ether, they didn't realize that a gas and a liquid and a solid are all made out of the same thing.
Right.
So their idea of a solid is the earth.
Yeah.
Their idea of the liquid
water
is the water. right? And the gas was the air.
Yeah.
Then eventually we realized, wait a minute, they're all made out of the same thing. And we called them states of matter.
Yeah.
They weren't different matter, they were states of matter.
Yeah.
And we actually have that problem right now today with light and electromagnetism and mechanics. We're thinking them as different bodies. But the first person who really started to give a name for electromagnetism as a body, just as in mechanics we have bodies, was really Einstein when he introduced the photon.
Okay.
So the photon was like a particle of light.
Gotcha.
Okay. And so that was the beginning of bringing these together in the sense that he at least labeled it as a body.
So we know what we're talking about. Yeah.
Okay. But we never had a word for a body that will actually apply to light and to mechanical bodies, because they're all just bodies that are interacting is really what it comes down to. So just as a gas and a liquid and solid appear to us very, very different, obviously light and other bodies seem very different to us.
Yeah.
But it doesn't mean that they're made out of different things.
Sure.
It just means that the states are different. Some of them are very light and not have very little mass. Some are moving really fast and some are moving slow. So the differences are, what's more important is the states of these bodies than what they're made of. And we're still today seeing light or electromagnetism and mechanics as completely separate things, not as one reality.
Yeah. See, that makes sense. That's palatable. So we've talked about particles. I want to talk about waves. Now, wave is one of those words that could mean a lot of things to a lot of different people. For me, a wave could be, someone waving, or the ocean. I think the water, moving waves, audio waves, sine waves, things like that. So help us understand what a wave means in the world of physics.
In the world of physics, a wave is just an oscillation, something that's moving up and down. And we have magnetic waves, we have electrical waves, and we have light. And so light is a wave. We don't really see the waves, although in some respects we do, because depending on how rapidly it moves up and down, we might see different colors.
Okay. Like the spectrum of a color.
That's right.
The frequency.
That's right. So the frequency is the frequency of the wave, and that gives us, we interpret that in our brain as different colors. A wave in electromagnetism is a light wave that is everywhere, that is spreading out and being distributed, everywhere. Even though we don't see it, we do, when that wave does reach our eye, we sense it.
The light waves.
Yeah.
And does this apply also to sound? Is the field of electromagnetics, does that also include sound?
No. So with sound, we actually have classically these tiny bodies that are all interacting, okay? And then they're all kind of propagating in a wave. Okay. And they're called longitudinal waves, which means the vibration of the wave is in the same direction that they're propagating.
Okay, that makes sense.
Okay.
Traveling in a direction.
That's right. They're vibrating in the same direction and that's a longitudinal wave. In electromagnetism, those are called transverse waves. As it's propagating in one direction, they're vibrating in directions that are perpendicular to it, and those are called transverse. Okay. So electromagnetic waves are still waves, but the vibration is transverse.
Okay, so how does that challenge our way of thinking? So we're going from particle to waves. Now we've got this whole new field, basically, of physics that's being discovered.
That's right. So, you have in 1687, you have Newton with his Principia. Now, if you go to 1873, we fast forward quite a few years, you have James Clerk Maxwell, and he publishes a book called The Treatise on Electricity and Magnetism. Okay.
That sounds like a good book.
And that's a really good book. And that lays out a discovery of his, which is really remarkable. So before Maxwell comes out with his book, you actually have the field of optics, or traditional light.
Dealing with light, visible waves.
Yeah, visible waves, and even to some extent, invisible waves.
Infrared.
Right, that's right. That's right. And then you have magnetism, okay?
Magnetic
like magnets.
waves. Yep.
Like magnets. And recognizing that magnets will give off waves too. Just a regular compass magnet will give off a wave, because that wave is responsible for why it can move something else. Okay, and then you have electricity, like the electricity in wires.
Current.
Yeah. So what Maxwell realized is that all three of them are giving off waves, and that all of these waves are traveling at the speed of light. And so he realized, wait a minute, magnets, optics, electricity,
It's a whole nother
nothing more
yeah.
than just these tiny bodies that are giving off waves that are radiating in a transverse waves that are radiating in a transverse direction, all near or at the speed of light. And so that what is born as a result of that book is this field called electromagnetism with its electromagnetic waves. Now, this idea of electromagnetic waves is a completely new idea of matter. It's more like energy,
Okay.
that is everywhere. So it's very different than particles. But it's also, just like particles were conceptually very easy to kind of get a feel for, the idea of just with particles that you have these particles, the world is separated by particles, there's nothing in between, that was this one idea. But now we have this new idea of these waves that are distributed through space, and that's also kind of a simple idea.
So more connected.
It's very connected where the other one is disconnected,
Yeah.
But a very different idea of what's really going on. So
It does seem in opposition.
They're very much in opposition. They're almost opposites.
Yeah.
So is reality really a bunch of particles that are acting, or is reality a bunch of waves that are all interacting in some way? So you now have two different fields, both each in their own having very instinctive features to them. They conjure up in one's imagination something that's quite tangible, each of them in their own way, but very different.
So when Maxwell was diving into this wave stuff, do you think it was a immediate crisis looking at the physics that we've already had with Newton and the particles, and then trying to rectify, wait a minute, this is completely foreign to what we've talked about up to this point?
It certainly heightened the crisis in the following way. Beforehand, you had this notion of particles, and we knew that mechanics with its particles couldn't predict things involving optics very well, or magnets, or electricity.
The math.
The math couldn't work.
Yeah.
That's right. And we had separate math for optics, separate math for magnetism, separate math for electricity. So they were all kind of separate. And then what he did is he brought those three together, the electricity, magnetism, and optics, all together into electromagnetism.
And that's his book.
And that's what he does in his book. And so now you have only two different ways of seeing reality. Okay, so it's a step in the right direction. We went from mechanics and three other fields to now mechanics and electromagnetism. So we're down to two.
Okay.
So at that point, I think it became clear to many people who are the theoreticians that there must be some connection between.
There's a gap.
There's a gap between the two, and kind of the race was on to try to figure out what's really going on logically. How do we bring together mechanics and electromagnetism? So in some respects, we call it a crisis, but it's also the opportunity became apparent.
An enlightenment to be discovered.
That's right.
So how does the wave innovations, the Maxwell studies, all of those things, did those have a direct impact on technology?
Electromagnetism is really driven by technology. The telegraph being the first device that really spreads the ideas of electromagnetism to the public.
So the technology comes first, and then the science.
Yeah.
And then the science improves on the technology.
That's right.
Kind of like a symbiotic.
Yes.
Okay.
Yeah, you really do see kind of during the days of Newton, you actually see mechanics. After Newton comes up with his Principia, we use those principles to develop solid mechanics and fluid mechanics and acoustics and all these fields that really lend themselves to mechanics really well.
Yeah.
And then with electromagnetism, when that all comes together, we really start to really understand all the interactions between magnetism, electricity, and optics, and that all comes together, and we have a much better notion of those three. So it's all progressing, but we're left with these two things.
Yeah.
And so, our sense of reality now kind of has a bipolar disorder.
That gap then, how long was that gap until you would say people started thinking about things like the fragment, things like that, and to try to find, I know we talked a little bit about, the quantum physics and the multiverse and all that stuff. How long was it before they collectively said, all right, we got to figure out the difference here?
Well, I do think that right after electromagnetism appears, the race is on for trying to find a unifying way to explain all of these things.
Okay.
So that becomes a very, very big push in physics. But there are a variety of barriers. You need a notion of a primitive. You need a building block that will work for both, for mechanics and electromagnetism.
Instead of two different ones.
Instead of two different ones. And also the field is relatively new. So after electromagnetism comes out, there's so much work working with that discovery that it's going to take time before one would move to something else.
Right.
So,
yeah, it's a brand new field.
Yeah, it's a brand new field,
Yeah.
and everybody's working in that area. So you have all this momentum going in that area. So it's going to take a while for that to happen. The first true discovery that brings together mechanics and electromagnetism is really Einstein's theory of general relativity.
Okay.
And that is where he introduces curved space-time, and using the same mathematics, he predicts the bending of light around the sun, okay, which is an electromagnetic phenomenon, and the precession of Mercury around the sun, which is a particle problem. So he's using the same mathematics to solve both a particle problem and an electromagnetic problem. But he uses very complicated mathematics with curved space-time. But that is the first time.
Was he able to do that?
Yeah. So he's able to do it successfully, and it truly is a tremendous achievement, because even though it's very, very complicated, he's successful.
Yeah.
So even though today, even if you're a physics major, you don't have to necessarily learn the theory of general relativity because it's so complicated, it still stands as the first time we ever saw that you actually can take mechanics and electromagnetism and bring them together.
Put them together.
Yeah.
Not necessarily having the fragment concept,
That's right.
but just in a practical sense, being able to justify the two together.
That's right. When Maxwell came up with his electromagnetism, he used also a very complicated mathematics. It wasn't just Einstein who used his curved space-time. When Maxwell developed his theories on electromagnetism, he used something called quaternions. Quaternions are a mathematical...
That sounds like a Star Trek word.
It is kind of...
Quaternion?
Yeah, quaternion.
Quaternion.
Yeah, quaternion, and it's this weird type of mathematics that is now mostly obsolete.
Okay.
Okay? And later on...
Why is it obsolete? Did it not work? Or
It worked, but it was extremely complicated.
Okay.
And it was replaced with a different kind of mathematics, which today we call vector math.
Yeah,
which everybody is familiar with.
Right.
But and vector math only came into being and became popular after 1910, 1915. And Maxwell does this before that. So at the time that he was developing his theories, the electromagnetism that we talk about today, he didn't use vector math, which is the way it's all, wasn't around yet.
Yeah.
He was using quaternion math. And so even some of these theories that you see historically that are invented don't necessarily use exactly the same math that we use today. Newton used fluxions, which is a form of kind of an early form of calculus.
Okay.
Maxwell, when he developed uses quaternions, Einstein, he used curved space-time. So all of them have used types of mathematics that were maybe unnecessarily complicated.
Sure. So when does calculus come in?
Well, calculus comes in after Newton. Newton is kind of known as the inventor of calculus.
Okay, so the raw version.
That's right. And then I guess the real question is, when does it eventually get taught in school?
Yeah, right.
And so certainly when I was a kid, calculus was never taught in schools.
Okay, so it's fairly recent.
Now calculus is taught, in some schools maybe, but today calculus is taught in most high schools.
To every high school senior's demise.
Yeah. I think most high school kids now are getting a little bit of calculus.
Mm-hmm.
Yeah.
All right, Larry, we're going to get to the good stuff. Paradoxes. Everybody loves a good paradox. What came first, the chicken or the egg? It's like this cycle of trying to figure out things. Your book, you talk about the 4 paradoxes. You talk about the paradox of continuity, force equality, mass equality, and the relativity principle. Tell me a little bit about those.
These are things that just don't make sense in classical science. So the continuity paradox has to do with the fact that theoretically in classical physics, things can go infinitely fast, but yet observation shows us that things are going up to the speed of light. So and the speed of light is not really a part of classical physics, so there's something missing there. And in fact, if things really could go infinitely fast, that would be one strange world. so that's one big paradox, and it's probably one of the biggest ones. The relativity paradox has to do with, is everything relative, or are things not all relative? You know? And in Newtonian mechanics, Newton makes the argument that actually things are not relative, that there's this one frame that's special called an inertial frame. And when we say that an object is going in a straight line with no forces acting on it, that will only be true in an inertial frame. Well, if it's the inertial frame, which frame is it? Well, why would there be one frame that's privileged, that would have the exceptional character that it's the only one that would work?
Sure.
Or only a family of frames would work. So that violates the idea that everything is relative, and so that creates a paradox or a question that nobody knows the answer to. The other thing that happens is we know in Newton's third law that body A produces a force on body B that's equal to the force that body B exerts back on body A. Why would those forces be equal? What made them equal?
Sure.
Was there somebody standing on body A orchestrating
Right.
To tell body B to make his force smaller while the other guy makes his larger to make them equal? There was no real understanding of why they would be equal. And the mass equality paradox has to do with the fact that there's two notions of mass. In Newton's second law, the force is equal to the mass times the acceleration. The mass, the larger the mass, the less the body accelerates. Mass, it impedes a body from accelerating. So that's called inertia, a lot of inertia, making it difficult
Harder to move.
But there's also mass in the gravitational law. So the mass is how strong a gravitational field is. And for some inexplicable reason, the gravitational mass was set equal to the inertial mass. Two completely different effects set equal to each other with no answer why that's true. So you have mass equality paradoxes, force equality paradoxes, continuity paradoxes, and you have relativity paradoxes. And so all four of those come out of the fields of mechanics and also impact electromagnetism. As it pertains to the fragment of energy, we can see why we had to move to fragments of energy by looking at the force equality paradox. That's going to be the one that's really important. That is the clue that tells us why classical mechanics with its particles and electromagnetism with its waves is missing something. The force equality paradox will give us the clue we need that will bring us to fields.
And are these paradoxes strictly theoretical, or are there practical ramifications of them?
So I think the practical ramification is where things don't make sense, and then afterwards where they do make sense. The best example that I can give is when we look at the Earth orbiting the sun as a good example. So let's try to imagine the Earth orbiting the sun. And what you see in the diagram is you see a small m, and the small m is the mass of the Earth. Okay. Then there's a large m in the center there. That's the mass of the sun. So you see the Earth kind of moving around the sun. Okay. And there's an equation there. The force that acts on the Earth is equal to a gravitational constant g multiplied by the mass of the sun and multiplied by the mass of the Earth and divided by the distance, the square of the distance between the two bodies. So r is the distance between the two bodies. So that's called the universal law of gravitation. And it's a formula. And that was, that was the last law that Newton had in Principia.
So that's what Newton came up with.
That's what Newton came up with. There's also the Newton's second law, which says that whatever the force is acting on the body, it's equal to the mass of the body that force is acting on times its acceleration, F equals ma.
Yeah.
Okay, so these are the two really most important laws. The problem with Newtonian mechanics was he didn't really define what a force is, and there was some ambiguity in what a force was. And so let me try to explain. We say that it's the force by the sun acting on the Earth. In words, the force F is the force by the sun acting on the Earth, pulling on the Earth as it's wanting to orbit, and forcing it to kind of orbit around the sun. But is the force really by the sun? Is the force acting on the Earth really by the sun? We say it's by the sun. If you look at the formula, you'll see that in the numerator, you have the mass of the sun and the mass of the Earth. If the force was really by the sun, how did it know the mass of the Earth?
Yeah.
So this is another paradox. In fact, you see a product of the two. You see the mass of the sun and the mass of the earth in there. In fact, if you were to ask a different question, instead of what's the force by the sun acting on the earth, if you asked what is the force by the earth pulling on the sun, the opposite, you'll get the same formula. F is equal to G big M small m over R squared. So you could ask the same question: how does the earth know what the mass of the sun is? So the earth somehow knows the force of the sun knows the force of the earth. So what does that mean? It means that the force wasn't really by the sun. It's not an action by the sun on the earth. And the force that's acting on the sun was not by the earth on the sun. It was really an interaction between the two.
So it didn't matter what the two were.
It didn't matter what the two were, and it really meant that
Which is why the formula could work.
Which is why the formula could work. So what it meant was, even though in words we say it's a force by the sun or a force by the earth, it's really an interaction between the two bodies.
So you could have a formula that works and have it still be wrong, or at least unknown.
That's right. What we had, what was unknown was the action by the sun or the action by the earth. We knew the interaction between them, and so our formulas worked because the forces were interaction forces, but they weren't action forces. They weren't really truly actions by the sun or by the earth. And when we eventually figured out what that action is by the sun and by the earth, that's what gave us field theory. That's where modern science comes in, when we actually isolate what the force was by. Let me just kind of go back to Newton's first law. So Newton's first law said, just go back to kind of the beginning.
In a vacuum, it's going to move.
In a vacuum, the particle is just going to move at a constant speed, constant direction. But then we said, okay, if it's not going to do that, there's another body external to it that's going to apply a force that's going to change its speed or change its direction. When we went from Newton's first law to Newton's second law to say that there's a force external to the body acting on it, we never really clarified, was that force truly by the other body and it had nothing to do with the body on which it acts, or was it an interaction between the two
bodies?
That's right. And that question was never answered by Newton. Newton never distinguished between an action by a body and an interaction between two bodies. And so this is what happened. It's really more clear to see that when I looked at that universal law of gravitation, we saw both masses in the numerator, both the mass of the sun and the mass of the earth, both of them in the numerator. Then we really could see, well, no, it's not really an action by the sun or by the earth. It's an interaction between the two of them.
Yeah.
Right. So then you start to ask yourself, okay, what is the action by the body? Okay. So I have a diagram here, and in this new diagram, what you can see is that the force by the earth is actually, and this is an action force. The action force by the earth only depends on the mass of the earth. And the action force by the sun only depends on the mass of the sun.
Regardless of the other body.
Regardless of the other body. So what you actually have is you've isolated what the action is by the body. Once you've isolated the action by the body, you basically, in a sense, have created kind of a function, a mathematical function of how strong that force is, okay, that only depends on that one body. And that is what we call a field.
Right.
Okay, that's what we call a field. So once you isolate
a single object and its force,
that's right,
regardless of what's around it, is the field.
Is the field, exactly. And so now what we realize is a better way to think about it. It's very subtle and it's not a big difference, but that difference is important because now what we're doing is we're saying that one body has its own field. And you know what else that body has? Its own energy.
Yeah.
So it has energy, the energy produces forces. We've now isolated how it's influencing other bodies, okay, so we've isolated it from body to body, and we now have fields that each of the bodies are generating. They each have energy, they each generate fields. We're now moving into modern science.
And who's responsible for this part?
Well, it's interesting. So the concept of a field the concept of a field was first expressed for electromagnetism, but was not in mechanics.
Okay.
Okay? So the field concept is a very old concept in electromagnetism.
With Maxwell?
With Maxwell. And even beforehand, Maxwell got it from a fellow by the name of Faraday.
Okay. Yeah, Faraday, yeah.
That's right. And so, and then Maxwell kind of organized the mathematics and made it all work. Okay. And now what we see is that field concept from electromagnetism transcends electromagnetism and really should be a concept that applies to both gravitation and electromagnetism. And so now what we have is kind of a common language that can be that works for gravitation and for electromagnetism. So now the differences between the two are starting to melt away. We're starting to see that, wait a minute, electromagnetism, gravitation aren't as different as we originally had thought. There's a lot more in common than we originally thought. So the field concept is an extremely important concept in modern physics. We often call it field theory. But really, it's really just isolating what the energy is that comes from that body, the field that it generates, which is not in mechanics.
Yeah. So how does that, where does that put us in resolution with the paradox itself?
Yeah, with the force equality paradox.
Yeah. Is it a different formula now, or?
Kind of. What really happened earlier is we had the force by the sun acting on the earth equaling to the force by the earth acting on the sun. It didn't really make much sense because you'd think that the force by the sun being so large compared to it, would be bigger,
greater, right.
But it wasn't. Well, when you isolate the action forces are proportional to their own mass. So the action force by the earth is much smaller than the action force by the sun. And now the forces are no longer equal, and it actually makes a lot of sense. But the forces that are no longer equal are the action forces. Okay?
Combined.
Okay. The individual, the separate action forces. The action force by the sun is huge compared to the action force by the earth. So this makes sense because the sun is strong and it should have a stronger force. Now what you do is you can define mathematically, from that, the action force by the sun multiplied by the mass on which the body acts, the earth, becomes the interaction force, or the force by the earth acting on the sun multiplied by the mass of the sun becomes the interaction force acting on the sun. So
you're getting the total force.
You're getting the total interaction.
The individual forces are different.
That's right.
So the interactive force is what that formula covers.
That's right.
Which is why it's no longer a paradox.
It's not a paradox because we know why they're equal now.
It's two different forces now.
Yeah, we know that we have two different forces, two different actions. We understand that they make intuitive sense because the sun force, the action by the sun is huge compared to the action by the earth. Yeah. We also see that when we multiply by the opposite mass that they'd be equal in magnitude.
Right.
So we basically now deduce from a simpler idea of action, which is actually intuitive, we deduce why the interaction forces are equal in magnitude.
Yeah, so you're always going to get, no matter what the two different forces are, the interactable force is always going to be those two multiplied.
That's right. You're always going to multiply one by the other, so the magnitudes are going to be equal. Not only that, because you're starting from fragments of energy, because you're talking that this is energy that's expanding out radially, it also follows that the forces will act along the line between the two bodies. So what ends up happening, one of the first consequences of starting with fragments of energy and action forces, is that you don't need Newton's third law. Newton's third law doesn't have to be stated as a law because it follows from the assumptions of starting with action forces, starting with fragments of energy. The Newton's third law becomes deducible from that. It follows naturally from the way we start. So we're starting in a much simpler way, and we're not having to invoke rules that we don't understand, don't know where they came from.
Right. So Newton's third law is right. It's just right for a different reason.
There's nothing wrong with it. There's nothing wrong with Newton's third law, but now it's self-evident.
Yeah.
Yeah.
That makes sense. All right, Larry. So we've covered a lot of stuff, and we're kind of distilled it down to this thing called the fragment, resolving that gap between the particle science and electromagnetism. We have this fragment of energy. What does this mean for our understanding of the universe and the practicality of it?
Well, I think a few things. There's kind of the perspective of the scientist himself. There's the average person who's maybe thinking about what is all of this. You know, when you look up
on your back porch.
When you look up and you ask yourself, what is all of this? We all know that there should be one explanation for these things, even though they might appear different to us.
Sure.
There's at the roots, at the heart of these things, there's one thing going on. And so the fragment of energy does a very good job of synthesizing the concept of the particle and the concept of a wave into this kind of point of light. And every point of light has a source, which is the modern version of the particle. And that source is radiating energy outside. And that is the classical notion of the electromagnetic wave. So we're now building up from these particles and waves. And from the point of view of the scientist, it might mean that that person can start to understand and do predictions a lot easier with quantities that involve particles and waves, and not have to go to different kinds of mathematical ways of doing things. But for the rest of us, we're not doing that.
Right.
The rest of us are just trying to imagine or think about what it is that's really, going on. So I think the fun part about this is we go and we look up at the stars and we realize after all of this science with particles and electromagnetic waves, that when we look up at the stars, we've saw the answer. Yeah. We see that star actually is the building block.
It's both.
That's right. It has a source and it's radiating out. Yeah. And then that is really the building block that is giving us, both of these things. But there's a little bit more to it than that. One more thing I think I would add to this. When you look at that star, it looks like a point of light. You just see a bright dot of light, okay? And then maybe a speck of light. But is it really a speck of light? You know that if we both got into a nice spaceship and you and I decided to travel to that star, it wouldn't look like a speck of light forever.
Yeah,
as we got closer and closer and closer, eventually the details of that star would come into view. So what does that mean? That means that it's no longer a fragment of energy. It's millions and billions of fragments of energy as it comes into view. So we have to remember that all science really is a model. And it's a model at a certain perspective.
Yeah.
So at one perspective, that sun is a single fragment of energy, and the universe is made up of all these fragments of energy from a particular perspective, and that's fine. But then as we move in closer, we're going to see the details of what it is that we're looking at, and it will no longer be a suitable fragment of energy. We'll now have more fragments of energy that represent it. So this gets back to the fact that what we do in physics is we model things at a scale, okay? And then as we
quantify it, you have to start somewhere.
Well, we actually, it's interesting. You might even think it's a disadvantage. Like, wouldn't it be great if science didn't have a scale? But if science didn't have a scale, didn't have a perspective, imagine how we think about things. Don't we always think about something at a perspective?
Yeah.
If we couldn't focus our attention to a perspective, we would have no way to focus.
Yeah.
And if we couldn't focus, we couldn't think.
It's funny because I play this game with my kids where it's 20 questions. And one of the questions I always ask, okay, it's an animal. Is it big? Well, is it bigger than a cow or is it bigger than an ant? Because it could be big depending on what you're comparing it to. But if you don't have something to compare it to, you don't know whether it's big or small.
Yeah, and if we really somehow had to assume information that was everything around us and it was independent of scale, it would be impossible.
Impossible.
And physics does the same thing.
Yeah.
Physics is at a scale. And so a fragment of energy is really a model, a point of light, which is a good model at a particular scale. So that would be the last thing I would say about all of this, is that when we went from particles and waves to fragments of energy, we were bringing together different ideas in physics, different fields of physics into one way of looking at things. But still, we should appreciate that that is still a model, and that model is still applicable only to one scale.
Yeah.
So we've been talking quite a bit here about different aspects of the fragment, but just to kind of sum it up, what we've seen here is that historically there is this concept called the particle, and it created an entire field called mechanics. We saw that there is 150 years later, electromagnetic waves hit the scene, and it had an entire field of its own. And that left us with two ideas, two very nice senses of reality, but they were very different. And then modern physics, in the face of those differences, had to decide how are we going to create kind of one sense of reality. The force equality paradox that I went through, where recognize that there is some ambiguity in the concept of force, that there's the action by the body and the interaction between the bodies. And once you understood what the action by the body was, you could think of that as generating a field. You could think of it having energy, and that body creating a force field and an energy field also. So we're no longer really talking about particles, and we're no longer talking about waves. We're talking about fields. And that concept of a field, as it pertains to just one body, captures both the concepts of the particle and the wave. The source, just like a point of light when you look up at the sky, that source is actually close to what we used to refer to as a particle. Mm-hmm. And the radiation that comes out of it is what is part of what we were talking about when we talked about waves. And so now what we have is these fragments of energy scattered through the universe that are together giving us a whole image of how we see and observe the world. And the last thing I guess I pointed out was that that fragment of energy is just a building block. It's from our own perspective. What could be just a single fragment of energy when you're really far away from something, when you get closer to it, could be a whole world in itself. Yeah. And it's really exciting because now we have this one way to think about reality. It isn't bipolar. It's actually this one way to kind of, when we look up at those stars, we're looking at reality not just far away, but all around us. Yeah. Whether we're looking inside the atom, whether we're looking at the macro scale, whether we're looking at the stars themselves. Really starting with fragments of energy and imagining the world that way is a much simpler and easier way to understand the universe. You know, it's so exciting. I had to write a book on it.
Yes. Well, I'm excited about episode 3, when we're going to talk about probably the most complex subject, which is time.
And we're going to make it easy.
I'll believe it when I see it.
Okay.